So as you've probably observed, the line between exponents and number properties is like razor thin. So one of their favorite things to do is to give you a bunch of exponent statements and see what kind of insights you can pull out in terms of number properties. Now, as it turns out, they have favorite insights and favorite inferences that they want you to nail, and we know what those are, so we're going to show them to you right now. There are actually a number of number property inferences you can make from exponents, and I detail more of them out in the companion guide. So please, please read the chapter in the companion guide as well as watching this video. But in the video, what I wanted to do was go through the most common and frankly the most powerful of the inferences. And it works like this. If x is an integer, then we know something about x squared. Each piece of DNA in x squared must be raised to an even number. And here's why. So x squared could be 3 squared times 5 to the 6th times 7 to the 4th times 13 to the 12th. And notice all of those pieces of DNA are raised to an even number. And when we square each side to get to x becomes 3 times 5 cubed times 7 squared times 13 to the 6th. Now I have no idea what that number is, but I know for sure that's an integer, and that's the whole point. X must be an integer. Now, notice this doesn't work if x squared is 3 squared times 5 to the 6th times 7 to the 4th times 13 to the 7th. Because when we square each side to get back to x becomes 3 times 5 to the 3rd times 7 squared times 13 cubed times the square root of 13. All right, again, I don't know what that is, but that is not an integer. And the whole point is that x must stay an integer. Now, the good thing about this inference is it's actually very powerful because it's not true just about x squared. This also works for x cubed or x to the 4th or x raised to whatever the rule is, that if each piece of DNA in x must be raised to a multiple of whatever power x is raised to, that's the only way to make sure that x is an integer. I know that sounds more complicated in English. It's actually fairly intuitive when we look at it in math. So let's take an example. Let's say you have x cubed. What we're saying is every piece of DNA of x cubed must be raised to a multiple of 3. So 3 cubed times 5 to the 27th times 7 to the 9th times 13 to the 12th. That works great because when we take the cube root of each side to get back to x becomes 3 times 5 to the 9th times 7 to the 3rd times 13 to the 4th. No idea what that is, but that's an integer. And the whole point is that x has to remain an integer. Works the same way with x to the 4th, except every piece of DNA has to be raised to a multiple of 4. So you have 3 to the 4th, 5 to the 12th, 7 to the 16th, 13 to the 36th. Works great because when we take the 4th root of each side to get back down to x, we have 3 times 5 to the 3rd times 7 to the 4th times 13 to the 9th. Again, no idea what that is, but that is an integer. And because this is true, they can ask you this. If a is an integer and a cubed equals 720b, what is the greatest integer that must divide b? And then we have our answer choices. Okay, now what are we being asked again? We need the greatest integer that must divide b. Now we've seen this language before, and what does that mean again? Right, it means when we make b as small as we possibly can, what is the biggest number that must divide into it? Okay, well, let's find out. So if a is an integer, we know something about a cubed. We know that every piece of a cubed must be raised to a multiple of 3. And you know what? There is something else in this question that we can spot. I see the word divide. And divide is code for get everything's DNA. And I see a big number there, and we don't have its DNA. We need the DNA of 720. And when you factor tree that down, and yes, factor trees are back in your life, I apologize for that again, we get 2 to the 4th times 3 squared times 5. Well, that kind of is a problem because we just got done saying that every piece of DNA of a cubed must be raised to a multiple of 3. And boy, 2 to the 4, 3 squared, 5? None of that is raised to a multiple of 3. Oh, do you know what though? B can solve the problem because a cubed must equal 720 times b. So if b contains 2 squared times 3 times 5 squared, I think that will allow all of the DNA to be raised to a multiple of 3. Remember, when we multiply numbers together, all we do is combine their DNA. So we will end up with 2 to the 6th because that is 2 squared times 2 to the 4th. We will end up with 3 cubed because that is 3 to the 1st times 3 squared. And we will also end up with 5 cubed because that is 5 squared times 5. Problem solved. We have all of the DNA raised to multiples of 3. And that, by the way, 2 squared times 3 times 5 squared is as small as we can make b. We can't make b any smaller because if we take any DNA out of b, we won't get everything raised to a multiple of 3. So that means b must be 2 squared times 3 times 5 squared. That equals 300. What is the biggest number that divides into 300? Well, 300. Our answer is D. Well done.